When an operating system crashes on your phone, you lose a game save. When it freezes on your PC, you lose an essay. For 99% of us, software bugs are nothing more than a minor inconvenience, a momentary irritation solved by a quick restart. But there is a hidden 1% of the digital world. Throughout tech history, a handful of operating systems were given direct, uninterrupted control over the physical world. They were trusted with our infrastructure, our weapons, and our very bodies. And they failed. From medical software that turned into an invisible executioner to an airborne OS that decided to dive bomb the ocean, these are the terrifying moments when a single line of bad code almost ended human lives. In the mid-1980s, the Therac 25 was celebrated as a miracle of modern medicine. It was a massive radiation therapy machine designed to destroy cancerous tumors with pinpoint accuracy. Older models relied on heavy, physical hardware interlocks, actual mechanical switches, and shields to prevent the machine from accidentally firing a lethal dose of radiation. But for the Therac 25, engineers made a fateful decision. They stripped away the physical safety nets and trusted everything to a built-in operating system coded entirely in PDP-11 assembly language. The OS had a deeply buried architectural flaw, a race condition. This happens when software tries to perform two operations simultaneously instead of in sequence. If a hospital technician typed in the commands to set up the machine too quickly, specifically, if they used the up arrow to correct a typo in under 8 seconds, the operating system got horribly confused. On the monitor, the OS would display a cryptic, minor error message, malfunction 54. It looked like a harmless glitch. The system didn't shut down, it didn't sound an alarm. But behind the screen, the OS had accidentally left the raw, unshielded electron beam turned completely on, blasting patients with up to 100 times the intended dose of radiation. Patients described feeling a blinding flash of light and an intense, invisible fire. Because the OS insisted everything was fine, doctors initially dismissed the patient's agonizing pain. Before the software bug was finally decoded and recalled, it severely injured multiple people and took the lives of 3. It remains one of the most chilling reminders of what happens when we blindly trust code over human instinct. It was the 25th of February 1991, during the height of the Gulf War. In Dhahran, Saudi Arabia, a makeshift barracks housed hundreds of American soldiers. Miles away, an Iraqi Scud missile tore into the night sky, hurtling directly toward them at Mach 5. Protecting the barracks was the Patriot missile defense system, a marvel of military engineering running an incredibly complex real-time operating system. Its job was simple: track the sky, spot incoming threats, and launch an interceptor. To predict exactly where a supersonic missile will be a few seconds into the future, the OS needs an incredibly precise internal clock. The software measured time in tenths of a second. But because of a microscopic math error in how the OS converted fractions into binary code, the clock lost a tiny fraction of a second every hour, specifically 0.95 seconds. To a human, that number doesn't exist. But this specific Patriot system had been left running continuously for 100 hours straight. By that 100-hour mark, the operating system's clock had drifted by a full third of a second. To a missile moving at thousands of miles per hour, a third of a second is an eternity, a distance of over half a kilometer. When the Scud missile roared into range, the operating system looked exactly where its math told it to look. But because of the time drift, it looked at an empty patch of sky. The OS assumed the radar reflection was a false alarm and completely deleted the tracking data. The Scud missile struck the barracks, 28 soldiers lost their lives and 98 were severely injured, all because a military operating system literally forgot how to keep time. On the 7th of October 2008, Airbus Flight 72 was cruising at 37,000 feet over the Indian Ocean, carrying 315 passengers. It was a beautiful day and the flight was perfectly smooth. Modern commercial airliners are entirely fly-by-wire. The pilot doesn't physically move cables to turn the plane. Instead, their joystick sends inputs to an operating system called the Flight Control Primary Computer, which decides how to move the wings. But high above the ocean, one of the plane's data sensors suffered a glitch and began feeding the operating system wild, contradictory spikes of data regarding the plane's angle. Instead of rejecting the obvious error, the operating system's processing logic choked on the data. It suddenly concluded that the plane was stalling and rising too fast. Without warning and without any input from the pilots, the operating system took total control of the aircraft. It violently pitched the nose of the plane downward, throwing passengers and crew into the ceiling. The pilots fought the controls, screaming to override the system, but the OS insisted it was saving the plane. It forced a second, terrifying nosedive moments later. Unbuckled passengers were hurled through cabin panels. Through sheer piloting skill, the crew managed to manually wrestle the plane down to an emergency landing in the Australian outback. While 119 people were injured, many severely, a catastrophic crash was narrowly avoided. The culprit, an operating system logic loop that refused to believe its own pilots. In 1997, the United States Navy wanted to build the ship of the future. They took the USS Yorktown, a massive, heavily armed guided missile cruiser, and turned it into a smart ship. They replaced hundreds of manual valves and controls with a centralized network running on a customized version of Windows NT 4.0. The goal was efficiency. The reality was a disaster waiting to happen. While navigating the Atlantic, a crew member was entering routine fuel valve data into the ship's database software. By mistake, the crewman entered a 0 into a data field. The application took that 0 and fed it directly into an underlying mathematical equation, forcing the operating system to do something computers despise: divide by 0. In a standard consumer application, dividing by 0 might crash your calculator app. But because of how the Navy's network architecture was integrated, Windows NT didn't know how to isolate the error. The error spilled over into the main memory buffer, causing a catastrophic cascade. Every screen on the bridge flickered and died. Suddenly, a multi-billion-dollar warship lost all propulsion, all steering, and all weapon control systems. The entire ship went completely dark, drifting helplessly in the ocean for nearly 3 hours. If the Yorktown had been in a combat zone or navigating a tight, rocky strait, the entire crew would have been completely defenseless, trapped on a floating piece of metal because of a basic math error. In June 1996, the European Space Agency prepared to launch the Ariane 5, a flagship rocket carrying a cluster of incredibly expensive scientific satellites. Decades of research and $370 million were resting on the launch pad. The rocket cleared the tower beautifully, but exactly 37 seconds into the flight, the rocket's guidance operating system encountered a problem. The software tried to convert a 64-bit floating point number representing the rocket's horizontal velocity into a smaller 16-bit signed integer. But the Ariane 5 was much faster than older rocket models. The velocity number was simply too massive for the 16-bit space allocated by the operating system. This triggered an integer overflow. The guidance computer immediately crashed. With its brain completely fried, the rocket's backup computer took over, but it was running the exact same operating system, and it crashed 1 millisecond later. The aerodynamic forces ripped the rocket apart, forcing the self-destruct sequence to trigger. A $370 million fireball rained down over the Atlantic Ocean. Thankfully, it was an unmanned flight, but it remains one of history's most expensive and spectacular software bugs, showing just how fragile our grasp on technology truly is. Today, people look back at the Y2K Millennium bug as a joke, a mass media overreaction where nothing actually happened. But the only reason nothing happened is because an army of software engineers spent billions of dollars and millions of hours fixing the core operating systems of the world before the clock struck midnight. And in the places they missed, the operating systems broke. In the early days of computing, digital memory was incredibly expensive. To save space, mainframe operating systems recorded dates using just the last 2 digits of the year. 1975 was stored simply as 75. When January 1st, 2000 arrived, legacy operating systems worldwide rolled over to 00. They didn't think it was the year 2000, they thought it was the year 1900. In Ishikawa, Japan, the operating system monitoring a nuclear power plant suffered a midnight crash, forcing radiation tracking equipment to fail. In the United Kingdom, a hospital's downdated OS miscalculated the ages of pregnant mothers, leading to incorrect medical risk assessments that could have cost newborns their lives. And in the sky over the United States, the primary air traffic control backup system for the entire country completely crashed. For a few tense hours, planes flew blind through the midnight sky, kept apart only by manual radio calls until engineers could patch the code. It wasn't a hoax, it was a frantic, last-second victory over a globally synchronized software death clock. Today, operating systems don't just run our computers and entertainment networks, they run our pacemakers, our autonomous vehicles, our electrical grids, and our global logistics. We live in a world built on code, held together by invisible digital logic, and as history has shown us, the line between a routine software update and a historic tragedy is often just a single line of bad math.